Welcome back to a new video lecture, and in this lecture we discuss a problem related with the Kani'S method. And already we discussed a problem of related with the Kani'S method in the previous lecture, and what are the steps is required for finding out the final bending moment, like fixed end moment value, then rotation factor, then the moment near end moment contributions through the iteration process, then last the final moments. So now we move on to our today's problem. So here you can visualize that analyze a cantilever beam using the Kani'S method. So here you can observe that at the joint A it is going to be fixed, then at the joint B, the joint C and the joint D are going to be roller supports are provided, and there is an overhanging portion is also provided in this question. So this is actually the difference from the previous question. Actually here the how to calculate the fixed end moment values, the modified fixed end moment value is going to happen over the overhanging portion. What's the influence of this roller support and this overhanging portion, that we'll observe or discuss in this particular question. So here you can observe that the 60 kilonewton is acting at a distance of 2 meters from the support A, and this BC portion, a UDL of magnitude 20 kilonewton per meter is acting, then a 40 kilonewton is acting at the center, then at the overhanging portion a 20 kilonewton is acting. So first of all we have to calculate the fixed end moment values. That you already know that the general equation. In the first case, the load is not acting at the center, so you have to use this equation, that is minus WAB square by L square. So if you work out, you will get minus 13.33 kilonewton meter. This unit is very important for each cases. Then MFBA, it is going to be positive, and this value is going to WA square B by L square. Then if you substitute, you will get 26.67 kilonewton meter. Then MFBC and MFCB, the values are going to be, the UDL is acting, so the general equation is going to be W minus WL square by 12, and you will get minus 60 kilonewton meter, and MFCB 60 kilonewton meter. And when you are going to this MFCD, the load is acting at the center, so you will get the general equation is going to be minus WL by 8, and here also the positive value WL by 8. And MFDE, if you are considering, can take that joint as going to be fixed as a cantilever beam, a load is acting, so you will get minus 20 multiplied by 2, you will get minus 40 kilonewton meter. Okay, so that's the case of the different fixed end moment values. And our next aim is to calculate the modified fixed end moment for that particular cases. So here you can observe that the DE portion is going to be overhanging, so and the moment which you obtained at the joint D, it is going to be minus 40. And we already know that if the joint, if you are taking a joint, obviously the final value it is going to be, if it is minus 40, then it is going to be plus 40. So the M of DC value, it is going to be plus 40 to balance that particular joint D. So in order to balance that particular joint, the M of CD value will change. So the fixed end moment of this M of CD is going to be the general equation M of CD plus 0.5 multiplied by net balancing moment at the joint D, or M of CD minus 0.5 multiplied by the unbalancing moment at the joint D. Any equations you can use. So at the joint D, you can observe that there is a minus 40 is acting here and plus 15 is acting here. So if you calculate, you will get minus 25 as your unbalanced moment. Unbalanced moment is going to be minus 25. So if you substitute minus 15, that is the M of CD value, and it is going to be minus 15 plus 0.5 multiplied by plus 25. Okay, the unbalanced moment is going to be minus 25. To balance, you have to put plus 25. Okay, that's the case. So if you substitute minus 2.5 kilonewton meter, and from this you can observe that M of CD is going to be minus 2.5 kilonewton meter, and M of DC and M of DE, or at the joint D, it is balanced right now with a plus 40 and minus 40. Okay, so that is the case of this modification of fixed end moment values. Okay, this step is very important. Okay, then coming to the next procedure to calculate the rotation factor. So from this you can observe that at the joint, if you are taking joint B, this far end is going to be fixed for BA and BC. So for EI by L general equation you can use. And in the case of BC, the moment of inertia value is going to be 2i. So you can take 2i in this both cases. And in the case of CD, it is going to be the end is far end is going to be hinged. So the general equation 3i by L you will use. Okay, so that is the case, and you will get the rotation factor. You have to use this formula minus half multiplied k by sigma k. Okay, k by sigma k actually a distribution factor. So minus 1 by 2 multiplied by k by sigma k, you will get these values. So in this case, the joint D is going to be already balanced, so there is no need to analyze again. So our need to analyze these joints is B and C only. Okay. So next step is to calculate the near end rotation contribution. For that, we will go move on to the different iteration processes. So first of all, you have to draw this diagram in this way, the boxes to be placed in this way. So at the joint A, you can observe that the fixed end, it is going to be minus 13.33. We already calculated, that is then 26.67 and minus 60 plus 60. Then here minus 2.5, the modified value you are going to use. Modified fixed end moment value you are going to use. And already this joint D, it is going to be balanced. So you can take 40 and minus 40. And after that, this you have to add up these values. 26.67 minus 60, then you will get this minus 33.33. Similarly, you have to add these two values and you will get this 57.5. Then the rotation factor also you have to mention at these both ends here and here also. Then our next step to start with our first cycle or at the joint B, our first cycle is going to be rotation factor multiplied by, that is minus 0.25 multiplied by sum of moments, that is minus 33.33, plus the far end moment at the joint A is going to be 0, and in the initial step at the joint CB is also going to be 0. So if you calculate these values, you will get 8.33. And here also the same value, since the rotation factor is same in both the cases. So 8.33 will obtain. Then coming to the joint C, here you can observe that how you got this minus 18.83. For that, you can see that minus 0.286 multiplied by, that is rotation factor multiplied by 57.5, that is sum of moments at the near end. Then the far end, that is going to be 8.33. Then here it is going to be 0. So at the joint D there is no values. So here if you calculate, you will get this minus 18.83, and similarly you can find out this minus 14.09. This is the first cycle. After that, the same procedures you are repeating, that is rotation factor multiplied by this minus 13.33 plus the far end contribution is going to be 0. Then this far end is you have to take minus 18.83, and observing these values you can each calculate, or iteration cycle number 2 can be completed, cycle 3 can be completed, and cycle 4 can be completed. And when it is close to each other, you can finalize your or stop, wind up your iterations. So and after that you have to take the last values. Okay, you have to take this last value for calculating the final moment. And also you can observe what are the calculations here followed. This is for the first cycle, we already discussed. You can easily calculate from the diagram itself, you can calculate each values, this near and contributions values you can easily calculate. So this is cycle 1, the various process at the joint B and joint C, you can already be calculated all those values. And coming to cycle 2, the procedures are same, exactly same procedures are the right equations we are using. Then cycle number 3 you can observe here. Then this cycle, last cycle, and with this cycle we will wind up the procedures. And now we will move on to our last step to calculate the final moments. For that, please arrange that joints, and here A, B, C, D and E are there, and then members A, B, B, A, B, C, which all members are connected to each joints CB, CD, likewise, all the joints is to be measured. Mark, then fixed end moment values, all values you got, you have to mention here, that is minus 13.33, then 26.67, minus 60, plus 60, minus 2.5, then plus 40, minus 40, and last overhanging portion there is no value. So, and we know that this joint D is actually balanced, so there is no need to calculate or further analysis is not needed. So near end contributions, you know that the final moment is going to be M final is going to be what? M final is going to be final moment. Fixed end moment M fixed plus 2 multiplied by Mij. Already we know that Mji foreign contribution. So that's why we are going to multiply each value with the 2. So 2 multiplied 13.4, then 2 multiplied by 13.4 again, then this value, the iteration final value which we are taking. Okay, so 2 multiplied minus 20.28, 2 multiplied by minus 15.17. After that, the foreign contributions, we already know that if you are applying a moment at this end, M is applied, so it will be carried over to this foreign is fixed M by 2. So the half the value will be transferred to here, so 13.4, here 0, and here minus 20.8, and here 13.4. Here there is no value, so 0 will be transferred here, and for these joints there is no more contributions required. And if you add up these values, you will get at the joint A it is very negligible 0.07 value, and at the joint B you can observe that the magnitudes are same and the sign is only different. At the joint C also 32.84 and minus 32.84, and at the joint D already balanced, my plus 40 and minus 40, and last 0. So, and with the help of these final moments you can easily draw bending moment diagram, and after that you have to calculate the reactions, and with the help of reactions draw the shear force diagram. And I hope the section is clear, and with this we wind up today's session. So thank you.